Let's talk about 1.2 exponents and radicals. So this all should be super familiar, but I also know that you did Algebra 1 and Algebra 2 during COVID. So let's see what we can't remember together. So for any real number, if we look at the nth power of a, that's just a to the n, and that means that you take a times itself n times. So that's what it means to be a to the n. So if we have an exponential notation, 1/2 to the fifth, that's just 1/2 times itself 5 times. So 2 times 2 is 4, 8, 16, 32. So this is just 1/32. Negative 3 to the fifth, that's going to be -3 again, times itself 5 times. But the thing to notice is every time we pair up two negatives together, it's going to make a positive. These two negatives make a positive, but then we have one negative left over. So that means I know this number is going to be negative. Anytime you have a negative raised to an odd power, it's always going to be negative. But then 3 times 3 is 9. 3 times 3 is 9. So really that's 81 times 3 is going to be 243. Now, this is different. How is this next one different? It is take 3 to the fifth and then make your answer negative. So this is 3 times itself, 1, 2, 3, 4, 5 times to get 243. And then at the very end, whatever you get, make it negative. So this is negative 243. You end up getting the same answer this time, but that won't always happen. So you need to be careful. Okay, let's do another example. So anytime you have 0 and negative exponents, anything to the 0 is 1. And then anything to a negative number just means 1/, that thing to a positive number. So for example, 1977 to the 0 is just 1, but 311 to the negative second is just 1/311 to the second. So 4/7 to the 0th power is 1. X to the negative 1 is 1/x. But then here, -2 to the negative third is 1/, that stuff to the third. But you know that that's just -2 times -2 times -2. So it's 1/8. So now let's look at our laws of exponents. These are very, very important. I assume you have these memorized. If not, you do need to memorize them. So if you take a number to an m, and that same number to an n, so if you multiply like bases, you add the exponents. So it should be a to the m plus n. And so then if you have 3 to the second times 3 to the fifth, it's just 3 to the, add the exponents, and you get 3 to the seventh. If you have a to the m over a to the n, you have a to the m minus n. And so this to the fifth over this to the second is just 3 to the 5 minus 2, or 3 cubed. So again, like bases, if you multiply, you add the exponents. If you divide, you subtract the exponents. Well, then if you have a to the m and then raise it to the n, you end up multiplying those numbers together. So if you take something to a power and then raise it again, you multiply those. So 3 squared, all that stuff to the fifth, is just 3 to the 2 times 5, or 3 to the 10th. If you have a product and then raise to a power, you can either multiply and then raise to the power, or you can raise each of them to the power and then multiply. So what this one is saying really is that order doesn't matter, or that you can kind of distribute the n as a way to think about it. So 3 times 4 squared, you would get 3 squared times 4 squared Again, if you have division, a divided by b, raised to the n, you can either divide and then raise to the n, or you can raise each to the n and then divide. So this to the n, this to the n, then divide. So order doesn't matter. Again, you can think of it as distributing the n here and here. So that's why 3/4 squared is just 3 squared over 4 squared. Then if you have a divided by b to the negative n, well, first thing you can do is that's the reciprocal of the inside, so it's b over a to the positive n. So if you have 3/4 to the negative second, you can rewrite that as 4/3 to the positive second. And lastly, if you have b to the negative m in the denominator, then it really wants to be b to the m in the numerator. And if you have a to the negative n in the numerator, it really wants to be a to the positive n in the denominator. So that means that 3 to the negative second on top wants to be 3 to the second on bottom. 4 to the negative fifth on bottom wants to be 4 to the fifth on top. And you can simplify from there. So let's see if we can't use our laws of exponents to simplify some of this stuff. Since we have like bases and we're multiplying, this is x to the 4 plus 7 or x to the 11. Again, like bases, this is y to the 4 plus negative 7 or y to the negative 3, right? But then we don't like negative exponents. That's one of the few things I'll harp on. I don't like negative exponents, so we rewrite it as, since this is y to the negative third over 1, this negative third really wants to be in the bottom, and it's 1 over y cubed. Next, if we have like bases and we're dividing, that's the same as subtracting the exponents, so we get c to the 4th. If we raise to a power and then raise again, we multiply those exponents. Well, then if we're multiplying and we have an exponent outside, we can distribute it, so we can get 3 cubed times x cubed is just 27x cubed. Similarly, if we're dividing x over 2 and we have it to the 5th, we can distribute that exponent and get x to the 5th over 2 to the 5th. But 2 to the 5th is just 32. Okay? So all that comes from having those exponents memorized. So now we get some that are a little bit uglier. Here in example 4, let's first start off by simplifying this. You want to work, here's a note, you want to work outside in. So from the outside in when you're simplifying. So first, I guess I distribute through this 3 to everybody. So I bring this along for the ride. And if everybody over here gets a 3, it'd be 3 cubed, a cubed, b to the 4th cubed, right? But, again, bringing this along for the ride. Inside here, that's just 27a cubed. But then if I have to the power and then raise again, that's b to the 12th. So going slow and steady definitely helps you get this problem correct. But then we're really just multiplying each one of these together, so we can put it in any order we want. I'm going to rewrite this as 2 times 27 times an a cubed times an a cubed times a b squared times a b to the 12th. So now it's really easy to see. These give you 54. These give you a to the 6th, and these give you b to the 14th, because we're multiplying with like bases. Again, notice how we worked from the outside in. So in this next one, yes, it does look really weird when you first look at it, but if we go one step at a time, working from the outside in, it'll all make sense. So let's first, when I look at this, I see this is stuff over stuff raised to the 4th. So 4th hits the top and gives me stuff to the 4th, and hits the bottom and gives me z to the 4th. but we bring this along. Oh, same thing here. This is just a fraction. This is just a fraction to the third. So it's a top to the third and a bottom to the third. So it's just x cubed over y cubed, right? But then I'm going to bring this along. It doesn't change. But now I'm going to distribute through. I have stuff raised to the fourth and it's multiplied. So because it's multiplied, I can say that's just y squared to the fourth times x to the fourth. Oh my gosh. It is really hot in here, by the way. So if I take y and raise it to the second, then to the fourth, I multiply to get y to the eighth. And I'm almost done. So on top, I really have x to the seventh because I multiply those like bases. But then here, I have y to the eighth divided by y to the second. That's really the same as y to the sixth on top. And then z to the fourth is chilling out on bottom. Again, notice how the more work you show, the easier it is. Not to say that these are easy. So let's do example 5. So first we're going to eliminate the negative exponents. So that means that this t to the negative fourth wants to be t to the fourth in the bottom, right? We still got a 2 down here and a t squared, but then this s to the negative second on bottom wants to be an s to the second on top. So now what we really have is 6s cubed. On the bottom you have 2t to the sixth, which is just 3s cubed, or t to the sixth. Next, for this to the negative second, there's a couple ways to do it. Well, we saw that we had a property that said if you have a fraction to the negative second, that's the same as the flip of it to the positive second. But if you have stuff over stuff to the second, you can just distribute in to the top and bottom and get the top to the second over the bottom to the second. But then on top you have stuff multiplied to the second, so you can distribute it through, and it gives you 3 squared, and then z cubed gets squared over y squared. But then if you have z cubed and then you square it, you just multiply those exponents and get z to the sixth. But then you know that 3 squared is just 9. Okay, great work. So the definition of the nth root. Well, here's how we're going to think about it. We're going to think about it as the nth root of a equals b. That just means that b to the n equals a. So in other words, let's look at this example. The fourth root of 81 is equal to 3 because 3 to the fourth equals 81. So the fourth root of 81 is 3 because 3 to the fourth is equal to 81. Similarly, the cube root of negative 8 is negative 2 because negative 2 cubed is equal to negative 8. So properties of roots, these are going to be very similar to exponents. Actually, it turns out, we'll see in a second, that a root is just a fraction exponent. So the nth root of AB, I can break up and take the nth root of A, the nth root of B. So that means that the cube root of stuff times stuff, I can take the cube root, and then multiply the results. So really this is saying order doesn't matter. You can either multiply and then take the root, or you can take the root of each and then multiply, whichever one is easier for you. You could take the nth root of A over B, so you can divide and then take the nth root, or you could take the nth root of both and then divide. So here, which one would you rather do? Divide this and then take the fourth root, or take the fourth root of the top and take the fourth root of the bottom? I think I'd rather do that. So you take the fourth root of the top and the fourth root of the bottom, and I know that the fourth root of 16 is just 2, because 2 to the fourth is 16. And the fourth root of 81 is just 3, because 3 to the fourth is 81. Now, if you take a root and then take a root again, we just end up multiplying those two. That should seem familiar. And then if you take, and this is where it gets a little interesting, so we don't see this one quite as much, but that's okay. So here, if you take the nth root of a to the n, they undo each other, and you get back a if your number exponent is odd. So in other words, negative 5 to the third is going to be a negative number, right? And then when you take the cube root, you're going to get the original back. Same thing for 2 to the fifth root is 2. But it turns out that if you have an even number, then you don't get the original number back when you take the root of a power. You end up getting the absolute value. So negative 3 to the fourth is just positive 81, and when you take the fourth root, you get 3 back. You don't get the negative 3 that you wanted. So when you have even numbers, the root and the power do not undo each other nicely. They screw up negatives, right? Will always give you positive. So for example, interesting. So the third root, if we wanted to think about how we might simplify some of this stuff with nth roots, the cube root, let's just go ahead and look at it. So one thing you might do is first, the cubed root, we know that the cube root of x cubed, it's going to undo each other and get x. So we look under here for the largest cube that we can find. So we rewrite it like this. And now the cube root of x cubed undoes each other, and that gives us the x out front, and then there's one left behind. So here, if we have 81, oh yeah, let me go back. So if you have 81 x to the 8th, y to the 4th, there's a lot of ways to do it. Here's a simple way to do it. Do you realize that 3 to the 4th is just 81, so that's how I rewrite that. X to the 8th is x to the 4th times x to the 4th. And then y to the 4th is just y to the 4th. And then we know that if you multiply things together and then take the root, you could actually just take the root and then multiply. So this ends up giving you a 3. This ends up giving you an x. This ends up giving you an x. And this ends up giving you a y. So we end up getting 3x squared y. Again, the book shows a different way to do it, but I think this is probably the easiest. Because it's a to the 4th, we're looking for anything to the 4th underneath, because the 4th root of something to the 4th is just that number back, right? Okay. I guess if we were being super perfect, I wonder if they said anything. Oh, I guess we did. Okay. So here, I'm just going to assume that x and y are positive. Just put that little note in the back of your head. That's why I didn't have to worry about absolute value. So I'm going to have to stop. No, I'm going to keep on going. The square root of 32 plus the square root of 200. You can only add these if you have like radicals. So I'm going to write this as the 32, I know is just 8 times 4. This is 2 times 2, and this is 2 times 4, so it's 2 times 2. So again, like we said earlier, that's a 2 to the 5th. So it's a 2. It's a 2 squared, and a 2. But then 200 is just, what? 20 times 10, that's 2 times 5, that's 4 times 5, and that's 2 times 2. So it's 2 cubed times 5 squared. So we should be able to do a factor tree if you can't already. So this would be 2 squared times 2 would be 5 squared. So anything that's squared can pass through the radical. The square root of 2 squared is just 2. The square root of this 2 squared is just 2. And we have a square root of 2 left under the radical. And then here, square root of 2 squared is just 2. Square root of 5 squared is just 5. And that 2 is left under the radical. So what you really have is 4 root 2 plus 10 root 2. So if you have 4 of something plus 10 of something, I guess that means you have a total of 14 of something. Similarly, here, there's an understood 2, so I'm going to rewrite this as the square root of 25b. Well, I know that 25 is just 5 squared times b. And then b cubed is a b squared times b. So the square root of 5 squared is 5 with the square root of b, minus the square root of b squared is just a b square root of b. So it's going to be 5 minus b, that many square roots of b. That's pretty ugly. Now I'm going to stop there.